Hello everyone. So in this video lecture I'm going to explain you first come first serve, that is FCFS process scheduling algorithm. So what is the main purpose of what is the outcome of out of this algorithm, that is to execute all the processes in efficient manner so that they all get CPU for its execution. And also we need to consider one point, that our CPU utilization should be maximum. Okay, so as you observe, notice this name, first come first serve. So whoever will come first and requires CPU, they will be served first. So let's go in detail. So selection criteria in this algorithm is the process that request first is served first. Okay, it means that process are served in the exact order of their arrival. Now in first point, that is request, there is term request. So request, that means particular process in the system is requesting for CPU, okay, for its execution. So whenever particular process request, it will be served first. If there is one process, it request after some another process, then definitely their process, that particular process will get CPU later after this first process. Okay, for example, let's assume that we are maintaining over here a queue of a processes that arrive in the I can say ready state. Okay, so this represent head and this represent tail, that means front and back. Okay, so this P1 that arrives first, after that P2 comes, and after that let's see P3 comes in the ready state. So obviously it should come after P2 process. Okay, so this is very simple. Generally in regular life or in day-to-day life, whenever there is a queue, we have to follow first come first serve order. Obviously, for example, if I am taking submission of student, okay, then they need to come in their order. Okay, just like that. And decision mode, that is non-preemptive. So what does it mean, non-preemptive? So non-preemptive nature, that means once a process is selected, it runs until it's blocked for an IO process or some other event, or it is terminated. So you just need to remember one point over here, non-preemptive, that means process is not interrupted until it is blocked for an IO or some other event, or it is terminated. Okay, for example, over here you can see P1 is running. Okay, let's assume CPU is allocated to this process. So if P2 arrive and this P1 is not completed, okay, if P2 arrives, then it will not affect the execution of P1. Okay, so this is non-preemptive. Yeah, but if P1 requires some input output, okay, then if this P1 is blocked, then obviously CPU will be switched to next process. Okay, but arrival of new process, remember my word, arrival of any new process will not affect current running process in non-preemptive nature. Okay, either it is terminated or it is blocked for an input output. Okay, or some other external event can be happen, but arrival of new process will not affect it. Okay, so that is the nature of non-preemptive. If I have assigned something to my process, then I cannot take back until it is blocked or until it is terminated. Okay, yeah, if I say this scheduling algorithm is preemptive, so what does it mean, preemptive? Preemptive means if P1 is executing right now, okay, and P2 comes, if P2 is of higher priority, then what will happen? CPU will be switched, it will be allocated to process P2. Why? Because it is of higher priority. That's why CPU will be switched to P2. And you can see though CPU was executing this process P1, it is switched to P2. So that is primitive nature. Okay. But non-primitive, that means once you have allocated CPU to the particular process, it cannot switch to another process on arrival of new process until it's blocked or it is terminated. Now implementation. This strategy can be easily implemented by using first in first out queue. Very easy. When CPU becomes a free process from the first position in the queue is selected to run. For example, if P1 is completed, then CPU will be allocated to process P2. After that, it will be allocated to process P3. Okay, after completion of particular process. Now let's see one example over here. So this is your scenario, or I can say a situation in the system. Okay, so basically you are given 4 processes: process P0, process P1, P2 and P3, and also arrival time. And you must notice this arrival time is mentioned as T0. Okay, and arrival time of this all the processes are also given. After that, CPU burst time is also given. Okay, which is labeled as, marked as a delta T, time required for completion. Okay, so what does it mean? Process P0 comes at 0 time and it require 10 unit for its completion. Okay. Process P1 arrive at time 1 and it require 6 unit for its completion. So it requires 6 unit. It requires CPU up to 6 unit. Okay. Now as you can see, this arrival time is given. Okay, so you have to build up a queue based on this arrival time. So in arrival time, which process comes first? Obviously P0, because its arrival time is 0. After that, at 1 P1 comes, after that at 3 P2 comes, and after that at 5 P3 comes. Okay, so you have to draw one Gantt chart. Okay, that will represent just arrival. It will just it is a kind of a chart in which arrival time and its execution is mentioned. Okay, let's see that. So at time 0, which process comes? P0. Okay, and as this policy suggests, whatever process comes first, it will be served first. Okay, so P0 first comes, so obviously this process will get first CPU. And how many unit it required for its completion? 10 unit. So what does it mean? This process P0 will be executed till 10. Okay, so 0 to up to 10, this process P0 will be executed. Now after that, P1 comes. After that, that is one point that I want to mention. When this process P0 complete, is it true that all the process has already arrived in the system when this process is complete? The answer is yes. Okay, or just look at this chart. Process P0 complete at 10. Process P0 completes at 10 unit. Okay, and all this process, so process P1 arrives at 1, so that means whenever somewhere here. Okay, process P2 arrives at 3, so somewhere here I can say, and process P3 at 5, so that means in the middle of its execution. So all the process has arrived. Okay, so once this process is completed, okay, the dispatcher will select the process. Actually it is a short-term scheduler. Okay, behind the scene it is this short-term scheduler that will select the process, and short-term scheduling scheduler will select the process based on particular scheduling algorithm. Okay, so if it is following first come first serve, then after P0's execution it will select the process P1 because it's arrive at unit 1, which is earlier to the earlier in compare to remaining process. Okay, so this one this one will be executed at 16 unit. It will complete its execution at 16 unit. Okay, why? Because it requires 6 unit. Over here you can see from this third column. Okay, so 10 to up to 16 process P1 will be executed. Okay, and now the question is, in this middle of its execution, can P1 it can be terminated? No. Okay, the answer is no. Why? Because this algorithm follows non-preemptive nature. So non-preemptive, that means process cannot be interrupted until it is terminated or some other external event occur. Okay, some arrival of some another process will not affect in its execution. So after that, P2 comes in the picture. Okay, so P2 gets CPU for execution, and this P2 has arrived in the system at time 3 unit, and it required only 2 unit. Okay, so you can see from 16 to 18 this process will be executed, and after that process P3. Okay, and it require how many units? It require 4 unit. Okay, so 18 to 22 this particular process will be executed. So you can see in this system process P0 has come first, after that P1, P2 and P3, and from the Gantt chart you can also see this process has been executed by the CPU in the same order in which they have arrived in the system. Okay, so that is why first come first. So now we have to compute some parameters. For example, what is waiting time, average waiting time, turnaround time of each process, and average turnaround time of this scenario. Okay, so let's calculate this. So finish time. So first of all you have to finish time, or I can say completion time, or I can say exit time. Okay, so when this process P0 arrive in the system, so that is 0. Okay, and it execute the CPU for 10 unit. So what is the finish time? So to find the finish time of the process, you need to check this Gantt chart. Okay, so P0 completed at the unit 10. So what is the finish time of process P0? That is 10, and you can see finish time is labeled as a T1. Okay, arrival time T0, burst time delta T, and finish time, that is T1. Now after that, let's calculate the process P for process P1. You can see it arrives at 1 and it requires 6 unit. So over here, once process P0 completed, P1 get CPU for its execution, and at 16 it will be finished. Okay, so this is the completion time of process P1. After that P2. So P2, you can see from the chart, P2 completed at 18, and after that process P3, which completes its execution at 22. Okay, now let's calculate turnaround time. Okay, so TAT, that is turnaround time. So there is one formula that is T1 minus T0. So T1 is your finish time, and T0, that is your arrival time. Okay, so you can see TAT. So for process P0, what is T1? That is 10, and what is T0? That is 0. So 10 minus 0, that is 10. For process P1, 16 minus 1. Okay, now 16 minus 1, that is 15. So basically turnaround time represent for how much duration particular process remain in the system. So you can see process P1 arrive at time 1 somewhere here. Okay, and it completes its execution at 16, and after that it just exists from the system. Okay, so it remains for 15 unit in the system. That is why T1 minus T0. Okay, after that process P2. So 18 minus 3, 15. After that process P3, 22 minus 5, that is 17. So okay, so this is, you have calculated turnaround time. Now after that, let's calculate waiting time of each process. Okay, so waiting time for process B. Now this waiting time represent how much time total, how much time process spent in the ready state, or I can say in the queue, to get CPU for its execution. Okay, so you can see when this process arrive in the system at time 0, and you can see from the chart this process gets immediately CPU for its execution. That means there is no waiting time for process P0. Okay, so over here this is 0, and the formula for waiting time is TAT minus delta T. So this is your turnaround time and this is your burst time. Okay, so you have to subtract TAT TAT minus delta T. Okay, so next calculate process for process P1. So what is TAT? That is 15 minus delta T. What is that? Is 6. Okay, so 15 minus 6, that is 9. After that, for process P2, what is TAT? That is 15. 15 minus delta 2 for this is 2, so 13. And after that, process P3. Okay, so 17 minus 4, that is 30. So we have calculated finish time, turnaround time, and waiting time of each process. Now we need to calculate average turnaround time and average waiting time. Okay, so average turnaround time, how can we calculate? We just need to summation of all this process divided by number of process. So 10 plus 15 plus 15 plus 17 divided by 4. Why 4? Because there are 4 processes in the system. So we get 14.25 millisecond. Okay, and what is average waiting time? So we have to perform summation of these values, 0 plus 9 plus 13 plus 13. Okay, divided by 4, so we get the answer, that is 8.75 millisecond. Okay, so if we consider this scenario, okay, this scenario, and we follow first come first serve policy, then average waiting time for process is 8.75 millisecond, and average turnaround time, that means in this much time process remain in the system, that is 14.25. okay, so that is the protocol, or I can say algorithm of first come first serve policy. Now let's see advantage and disadvantage, pros and cons of this algorithm. So it is very simple and fair, easy to implement, easy to understand also. Okay, every process will get a chance to run, so starvation doesn't occur. And what is the disadvantage? So no efficient, because average waiting time is too high. After that, convoy effect is possible. That means all small IO bound process wait for one big CPU bound process to acquire the CPU. After that, CPU utilization may be less efficient, especially when a CPU bound process is running with many IO bound process. Now, when IO bound process, that means particular process require input output. Okay, and whenever particular process require input output, then it will be blocked. Okay, it will be blocked. So for that particular scenario, the CPU utilization is it may be decrease. Okay, so that is the disadvantage of this policy. So that's all about first come first serve. Okay, and this is just I have explained how it's work, how to what you need to calculate, how you can calculate these values. Okay, so if you want to make it very easy, then you just need to practice it. Okay, so I hope you understood it. Bye bye, enjoy.